Systems were some of the first types of PV systems to be installed, mostly in remote applications where electricity from a public electrical grid was either not available or not practical or desired. In this lesson, we're going to talk about what a standalone system is and where they are commonly used. We will also look at the different pieces of equipment that are found in these systems, and we'll discuss how energy flows through a standalone system. Any PV system that functions independently and is not connected to a larger utility grid is called a standalone system. PV direct systems, which consist only of PV modules and the load they are powering, are one form of standalone system. In addition to the PV modules, a standalone system can power DC and/or AC loads, depending on the application. There will also be some type of storage, likely a battery, which will be used to store energy that is generated during the day for use during the night. A charge controller is used to regulate the charging and discharging of the battery to make sure it is not damaged from over or undercharging. An inverter is also used to change DC electricity to AC electricity and allows the system to power any conventional AC loads. A standalone system can be designed to power only DC loads, in which case an inverter isn't required, or it can be designed to power AC loads or both DC and AC loads, as we see on the slide. Inverters have to be carefully selected to match the intended use, and they have to be able to function within the parameters of the other components in the system. Everything has to be compatible. For example, it's important that battery-based inverters are selected to match the voltage of the battery bank they are connected to. The most common battery bank voltages are 12, 24, and 48 volts. However, it is becoming increasingly more common to see higher voltage batteries, so be on the lookout for those. It's also important that the selected inverter has a power or wattage rating high enough to provide for all the AC loads, including any start or surge loads associated with some types of appliances, such as motor loads. When a battery needs to be charged in a standalone system, any available DC power from the array flows to the batteries through the charge controller, which regulates and manages the charging process. If the batteries are fully charged and the sun is shining, any power from the PV array will be used by the loads. If the loads need more power than the PV is providing, the batteries can provide the difference. At night, the battery will supply power to the loads. A standalone system has to be properly designed to provide enough power for the intended use so that the user doesn't run out of power during the night or during prolonged periods of cloudy days. So the slide shows a very simplified power flow diagram of what a standalone system looks like at night. The batteries will provide the power for any DC loads and for any AC loads as well, and of course that will have to go through the inverter. In a standalone system, the PV array is our generation source. The consumption would be the AC loads through a panel and the DC loads through another panel. Storage would probably be in the form of a battery bank, and conversion will happen in the inverter. Often an additional charging source is included with standalone systems as a backup to ensure that the batteries can be charged when there isn't enough sunshine to do the charging. Having an additional charging source will reduce the chances that the user will run out of electricity during cloudy periods. Backup charging systems, such as the AC generator we see on the slide, can also increase battery life by making sure the batteries are not too deeply discharged and are fully recharged on a regular basis, which is necessary for some battery types such as lead acid. Inverters that are used in standalone systems with additional charging sources are inverter chargers, which means they're capable of inverting DC to AC energy as well as converting AC to DC, and that can allow an AC generator to charge the DC battery bank. These inverter chargers can typically only work in one mode at a time, either charging or discharging. When they're charging the battery using AC power, they are also usually capable of also supplying the AC loads. Backup generators can be turned on manually or automatically and are commonly fossil fuel based using propane or gasoline. In a standalone system with a backup generator, we have two generation sources. We have the PV array and also the AC generator. We have the same storage and conversion that we had in the previous system. And we also, of course, have our consumption, in this case in the form of AC loads and DC loads. Because standalone systems can be designed to operate with or without an inverter, they can be very simple or very complex and can be used in a variety of applications. We can see a few examples on this slide. Up on the left, a remote cabin may have a battery bank and a charge controller with AC and DC loads and an additional backup generator. A medical clinic, as seen in the upper right, may have a refrigerator to store vaccines that is powered directly by DC and only requires a battery and a charge controller. Other examples of standalone systems include RVs, boats, street signs, remote weather or communication stations, and landscape lighting. In some cases, multiple renewable generation sources can be included in a standalone system. We refer to these types of systems as hybrid systems. Some PV systems may include a wind generator because wind and solar tend to complement each other. When the sun's shining and it's relatively calm, the PV may be sufficient to charge the batteries. However, on days when the weather is stormy or at night, when the wind is blowing, a wind generator can do the work of charging the batteries where the PV array cannot. A wind generator will have its own controller, which will prevent the batteries from being overcharged. Micro hydro turbines are another renewable generation source that can be incorporated into a standalone system when you have a reliable flowing water source. In a hybrid system, we have multiple sources of generation as well. In this case, it's a wind turbine and a PV array. We have our same storage and conversion components, as well as our consumption, in the form of an AC service panel in this case. These types of systems can also be set up to service DC loads if desired. We can see a few examples of hybrid wind and PV systems on this slide. With multiple charging sources, there is less likelihood that a system will run out of power. Keep in mind, the more equipment that is added to a system, the more complex the system becomes. Design, installation, and maintenance becomes more costly. In this case, you can see in the photos there is a PV array mounted on a pole, in both the cases on the left, and there's a wind turbine in the background. On the right side, it's a similar setup. Those PV modules and that wind turbine on top of each pole presumably powers the lights to which they are connected. As we've seen in this lesson, standalone systems are PV systems that operate independently and are not connected to a larger utility grid. Standalone systems usually incorporate some form of storage, such as batteries, and they can power AC and DC loads. Fossil fuel generators, wind turbines, micro hydro turbines, and other sources of power can also be incorporated into a standalone system to help keep batteries charged and healthy.